All right, in section 3, we're going to be talking about starting to solve exponential equations, and we're going to do that in this section using what's called the exponential law. Now, an exponential equation is going to be really any equation with a variable in the exponent. Now, some of these can be really easy. For example, if I have, say, 2 to the x power equal 4, well, if we just think about that, 2 to what power is 4? Well, that would be 2. So x equals 2 would be our solution. Because just like any equation, we're trying to figure out what x makes the equation true. Other ones are not so easy. If I have something like 2 to the x equals 5. Well, 2 to what power would give us 5? That is actually not a nice number. Because we know 2 to the second is 4. 2 to the third would be 2 times 2 times 2, which is 8. So this x value is somewhere between 2 and 8. But for right now, we don't really have a method to solve that. So what we're going to do in section 3 and beyond is we're going to actually start to talk about how to solve these equations for the variable x. So the first way we'll do that is we use what's called the exponential law. So the exponential law says this. If we have an equation, so if we're given an equation, and we'll say it's b to the big X equals b to the big Y. Okay? Now notice what's very important about this is we have two b's that are the same. So if b to the x equals b to the y, then x equals y. So if we have the bases the same, so if we have 10 to the x equals 10 to the 2, really we can just ignore the bases and just set the tops equal, so it would just be x equals 2. So if the bases are the same, you could just set their exponents equal. This is what's called the exponential law. Now we will do a lot of examples where they are equal, and we'll do other examples where they are not equal. So let's look at a couple examples here. So the first one says we have 10 to the 2x equals 10 to the x plus 8. Now the first question is, do these have the same base? They do. They both have a base of 10. So since their bases are the same, we can just set their exponents equal. So the exponent in the first one is 2x. The exponent in the second one is x plus 8. So we really are left with the equation 2x equals x plus 8. So to solve this, I will subtract x to both sides. So 2x minus 1x is x. This would cancel, and this would just leave us 8. So x equals 8 would be the solution to this equation. We can check it to make sure it's correct. So if we plug it in, we have 10 to the 2 times 8. We want to know if that is equal to 10 to the 8 plus 8. Well, we know 2 times 8 is 16. And we know 8 plus 8 is 16. So that is our solution. So just like any other equation, you can always plug it in and check. Okay, let's look at another example. We have 1/3 to the 5x plus 6, and we have 1/3 to the 2x. Again, key statement in this problem, we both have a base of 1/3. So since these bases are the same, we just set the exponents equal to one another. So 5x plus 6 equals 2x. And we'll do basically the same thing. We'll solve for x, so I'll subtract 5x from both sides. That will give me 6 equal negative 3x, because 2 minus 5 is negative 3. I will divide both sides by negative 3. So 6 divided by negative 3 is negative 2. So if the bases are the same, awesome. Very simple to do. You set the exponents equal, you solve it, and you're done. But unfortunately, not all the time will the bases be the same. So the question is, if we have different bases, How do we work with those? Well, to do this, we'll have to use some basic knowledge about numbers, and we'll also have to use some of our exponent rules we learned in Algebra 1. So one of the biggest rules we're going to have to remember is what's called the negative exponent rule. Now, if you recall, the negative exponent rule said this. If we have a to a negative power, we'll call it m. If we have a to the negative m, that is the same as saying 1 over a to the positive m. So if we have a negative exponent, instead of having the base of a, we take it 1 over a, and then our exponent becomes positive. Or vice versa, if we have 1 over a to the m, it can work in the opposite way, and we can write this as a. So if we flip the a, if we flip this base, then this would just become to the negative m. So this will be a process we'll have to use a little bit, but this is just one of the exponent rules that you should know from Algebra 1, but I just wanted to remind you if you had forgotten. So the key thing is in this section, since we only have one way to solve exponential equations, and that way is to get both of the sides to have the same base and then set the exponents equal using our exponential law. If we don't have the same base, we have to make them the same base. So we'll do that by just changing them up a little bit. So let's look at our first example. We have 3 to the x equals 27. Now the base on the left is 3, and the base on the right is 27. Well, that does not work. What we'd like to see is can we rewrite these both as the same base. Now 3 really doesn't change too much. 3 is 3. Okay, so I'm really not going to be able to change 3 to any other value. Now 27 I can change. If you think of what 27 is 3 times 9. It's 3 times 3. So 27 is 3 times 3 times 3. Or we could say 27 is 3 to the third power. So in our equation, since we know 27 is 3 to the third, if I replace 27 with 3 to the third, well, all of a sudden now my bases match. And because my bases match, I automatically can use my exponential law. So I would just take the exponents, x equals 3, and we're done. So let's look at this one. So we have 4 to the 10x, and we have 8 to the x plus 3. Those are not the same. So I can try to figure out if I can write these as a different base. So I'll try to take them down to prime numbers again. So if I take 4, I know 4 is 2 times 2. So 4 is 2 to the second. So I have a base of 2. So I'm going to try to do the same with 8. So 8 is 2 times 4, which is 2 times 2. So we have 1, 2, 3, 2. So 8 is 2 to the third. So what we now have is I can replace the 4 with 2 to the second, and I can replace 8 with 2 to the third. So if I do this in the equation, so instead of 4, I'll put 2 to the second, but then I'll still, so I have 2 to the second, but then I'll still have my 10x on the outside. And then if I do the 8, I'll make that 2 to the third, but then I have the x plus 3 on the outside. Okay? So now we have the 2's that are the same, but everything that's an exponent will have to go in the exponential law. So that second power and that third power we have will now be part of our problem. So I'll write this as 2 times x, because I take away the base, equals 3 times x plus 3, so I'll make sure I put that in parentheses. So I have 2 times 10x equals 3 times x plus 3. 2 times 10 is 20x. I'll distribute the 3, so that gives me 3x plus 9. So I will subtract 3x from both sides. So that gives me 17x equals 9. I'll divide by 17. So x is 9/17. Kind of an odd answer, but exponential law says that's what it is. It's what it is. So this is one where we'll have to use our negative exponent rules. So if you think of 25, 25 is simple. That is 5 times 5. So 25 is 5 squared. Now 1/5, we could think of this as 1/5 to the first. Well, since this one above, the 25, has a base of 5, I would like to rewrite this one as a base of 5. Well, from our exponent rule from above, it says if we flip the base, we can do that. We just turn the exponent on the outside to negative. So 1/5 is really the same as 5 to the negative first. So if I replace those, I have 5 to the negative first to the x, and I have 5 to the second times 6x. So if I take what I have negative 1 times x, which is negative x, equals 12x. So in this case, there's lots of numbers, or lots of x's, but no numbers. So I'll get all the x's on one side. I'll add x to both sides. So I get 0 equals 13x. And I'll divide both sides by 13. So x is simply 0. I can check. Anything to the 0 power is always 1. So 1/5 to the 0 would be 1. And 25 to the 0 would be 1 as well. But the key thing is trying to get those bases to be the same. Okay, let's look at our last problem. We have 7 to the x equal negative 30. Now when you first look at this, if I take 7, well that's just 7 to the first. There's no way I'm breaking that down. If I break down 30, well 30 as prime numbers could be 3 times 2 times 5. So really no repeating numbers that kind of make it so we can write it 7 to the power. So we really cannot use exponential law here. But I can still solve this. In fact, I actually know this problem is no solution. And here's why. If I have 7 to the x, no matter what value I put in for here, any x value, no matter what you pick, negative, positive, rational, irrational, 0, it does not matter. Any x value will make this positive. We'll make 7 to the x positive. So you can never have an exponential equation equal to a 0, to a negative. So this number can never be negative, ever. Because any 7 to any power will always be positive. Alright, so again, pretty simple law. Get your bases to be the same. Set your exponents the same. So if you have questions, please let us know.